So this section is going to look at how do we actually find limits, basically algebraically, and we use limit laws to do that. So we have to understand what those limit laws are. You don't have to use limit laws only algebraically, but they're useful for doing things algebraically to know them. So here are all the limit laws. This one just says the limit of a sum and difference is the same as the sum of the limits and difference of the limits. The limit of a constant times a function, you can pull that constant out front. The limit of a product is the product of the limits. The limit of a division is, or the limit of a quotient is the quotient of the limits, provided that the limit at the bottom exists. If it doesn't exist, then you can't do this. Actually, what I should say is it doesn't equal 0. It can not exist, but it can equal 0. This one is that the limit of a function to a power, you can take the limit of the function and then take that to the power, as long as you've got a positive integer. The limit of a constant is just a constant. The limit of x as x goes to a is just a. The limit as x goes to a of x to the n is just a to the n. The limit of this nth root of x is just the nth root of a, provided that n is a positive integer. If n is even, then your a better be positive or not 0, or 0. Can't be negative. So a non-negative number needs to be in here. Your a can't be a negative number if n is even, because you can't take the square root or the fourth root of negative numbers. And then this one just says, it's similar to this one, if you got the limit of an nth root of some function, you can pull the nth root out and find the limit first and then plug it in. So these are all our limit laws, and we're going to use these limit laws to find some limits. This one actually is going to be using a graph to try to figure out what the limits are. We're still going to use the limit laws to do this. So this one, first one is asking us to find the limit as x goes to 2 of f of x plus g of x. This is f of x, and this other function is g of x. And so again, I'm going to use limit law 1, which says I can take and divide these up into two different limits. So do the limit as x goes to 2 of f of x plus the limit as x goes to 2 of g of x. So that's the limit law. Now we're graphically going to do this one because we don't have the actual algebraic functions, but we do have the graphical function. So as x goes to 2 of f of x, it looks like we're heading towards the number 3. All right. Or 2. My graph isn't exactly perfect. Let's say it's heading to 3. And as x heads to 2 on g of x, as we're getting closer and closer to 2 at both sides, it looks like we're heading to the number 2, number 0. So we get 3 plus 0 is 3. Now let's do the same thing with the limit as x goes to 1. Again, I'm still going to use limit law 1. So I just put a little 1 there just to remind me that I use that limit law. So the limit as x goes to 1 of f of x plus the limit as x goes to 1 of g of x. So up here, as I'm heading towards 1 on my f of x, it looks like I'm heading towards the number 1. So it looks like this is 1. Now let's head to 1 on g of x. As I head from g of x from 1 from the right, I'm heading towards the number 1. As I head towards 1 from the left of g of x, I'm heading towards the number 2. So as a reminder, that means that the limit from the left and the limit from the right are not hitting the same numbers, means we can't match up. Then we do not exist. So this one does not exist. Since that one does not exist, the whole thing does not exist because you can't add a 1 to a does not exist number. All right, let's try this one. This is limit law number 5. It's the limit of a quotient. So it's the limit as x goes to negative 1 of f of x over top of the limit as x goes to negative 1 of g of x. And so looking up here, as x goes to negative 1 of f of x, we're looking like we're heading towards, if we come from both directions, it looks like we're heading towards the number negative 1. So this one looks like it's negative 1 in the top. Now let's look at the bottom for g of x. As I'm heading towards negative 1 for g of x, it looks like we're heading towards the number 0. But in that limit law is since we can't have 0 in the denominator, then the limit can't actually equal 0. So this means this one does not exist because you can't have 0 in the denominator. A little bit later on, we're going to tell you that this actually would be, in this case, negative infinity, because -1/0 actually is tending towards negative infinity. But right now, we're just going to say it does not exist. All right, and let's do this one. Again, I have two things multiplied together, so I can take the limit of the first times the limit of the second. So this is limit law number 4. You don't have to always say which limit law it is. It just helps you to see what we're doing. Then when I look at this one, I notice, hey, this is a little bit more involved. So now I'm looking at limit law number 9. Limit law number 9 says that this would be 2 to the 3rd. And this one would be f of 2. So again, I'm looking to see where we're heading to as x heads to 2 on my f of x. As we're heading to 2 on my f of x, it looks like we're heading towards the number 2. So we end up with 16. All right, so that's where we can use graphs to kind of figure out what it is. Now let's do another one where we're actually going to just use the limit laws to find out what this is. Noticing again, I've got a product. So I'm going to use limit law number 4, which says I can do the limit of the first and then do the limit of the second. Then I notice that I have a limit of something to a power. So I can actually find the limit as t goes to -1 of the t squared plus 1 and then raise that to a power. This is limit law number 6. Same thing with this one. I have a limit as x goes to -1 of t plus 3, and I'm going to raise that to the 5th power. Now I notice I have a limit of a product, a limit of a sum. So I can use limit law number 1, which says that I can divide those limits up. And again, normally we don't do this much, but I just want to show you, oops, limit law number 1, not number 6. I just want you to see what we're doing here. So that would be the limit as t goes to -1 of t squared, plus the limit as t goes to -1 of 1, and that's going to be raised to the 3rd power. And then same thing here, we're going to have the limit as t goes to -1 of t, plus the limit as t goes to -1 of 3, and that's going to be raised to the 5th power. So we use limit law number 1. Now we're going to use limit law number 9, which says the limit of t to a power as t goes to -1, it's just going to be -1 to the 5th power. That's again limit law number 9. The limit of a constant is just the constant. So that's limit law number 7. And that's being raised to the 3rd power. And then we're going to multiply that. We have limit as t goes to -1 of t. That's limit law number 8. And then again, we have a limit of a constant. That's just going to be the constant. That's limit law number 7. And now we just have numbers. So now we're no longer limit laws. Now we're just going to find out what all of these are. And we calculate this. We find out that we've got, how did I write to the 5th? That should be to the 2nd power. Second power. So we got -1 squared, which of course is 1, plus 1 is 2. So we've got 2 cubed. And then we have -1 plus 3, which is 2. We have 2 to the 5th. So we end up with 2 to the 8th. And that's your limit. Again, we don't go through all of that. We're actually going to use what we call a direct substitution property. The direct substitution property says if f is a polynomial or rational function and a is in the domain of f, then the limit as x goes to a of f of x is just f of a. All we have to do is plug it in. And this comes from the fact that we have polynomial functions and we can use these limit laws to kind of simplify these. So this is a very nice, useful one, provided we're in the domain. So the first thing to do is to actually find the domain of this function. So let's go ahead and find the domain of this function. And the domain, remember, you can't have 0 in the denominator, so x squared minus 4 can't equal 0. So x can't equal -2 and 2. So the domain is all real numbers except 2 and -2. Well, the problem is that this one is letting x go to -2. So I can't use the direct property that we just talked about, direct substitution property, because I'm not in the domain. My a is not in my domain. So I got to figure out something else to do instead. If I tried plugging it in there, I get -2 plus 2, which is 0, over -2 squared minus 4, which is 0. I'd get 0 over 0. Again, 0 over 0 is what we call indeterminate. We don't know what that is. It's not 1. It's not 0. It could be anything. So that's why it's called indeterminate. We don't know what it is. So I'm going to go ahead and maybe do a little bit of algebra before we go to find this and see if we can find out what this might be. So let's see if we can do a little bit of algebra here to simplify this just a little bit. The top is already factored, but the bottom I notice does factor. X plus 2, x minus 2 is how that factors. So then I notice, hey, there's a plus 2 here and a plus 2 here. They can cancel. So when I do that, I get the limit as x goes to -2 of 1 over x minus 2. Well, now the domain of this new function is x equals all real numbers except 2. So -2 is in that domain. So I now can just substitute in. So now I can use the direct substitution property because I was able to simplify my function into one that would allow me to plug that -2 in. So we get 1 over -2 minus 2, and that gives me 1 over -4. And by the way, 1 over -4 is -0.25. And we did this one numerically in a previous video and graphically, and now we can see algebraically what exactly it's equal to. All right, let's do another example. In this example, we're going to have a piecewise function. H of x is equal to x squared plus 3 as long as x is not 1. If x equals 1, we're equal to 4. We're going to take the limit as x goes to 1 of h of x. And the main thing to remember about limits is we're not letting x equaling 1. We're letting x get closer and closer and closer to 1. So x is not 1. So if we do this, we're actually using the top equation here because x is not equal to the number 1. It's tending towards 1. It's going to get closer and closer, but it never is actually equal to the number 1. So because of that, we can actually use the top equation and use, again, direct substitution. So now we have the limit as x goes to 1 of my top function, top branch, x squared plus 3. And I can then use direct substitution that allows me to plug that in. So using direct substitution, that would be 1 squared plus 3, or 4. If you want to look at the graph of this, you could graph this up. We'll go ahead and graph it up on Desmos. If I graph this up on Desmos, we get x squared plus 3. And this is what the graph looks like. But remember, at 3, whoops, let's change our window a little bit here. Change the window just a little bit. Maybe have our x's go all the way up to, I don't know, 15. And so as we're heading towards 1, we're heading towards, it looks like the number 4. Now, there, you can't see it, but there is a hole here. There's a break here. It actually may not be a hole, but when x is less than there, when x is not 1, we'd look like this. When x is 1, we'd actually be the number 4. So there actually would be just a solid dot here. But you can see we're heading towards the number 4. So if we looked at the graph of that. All right, another example. Let's find this limit. So we're finding the limit as h goes to 0 of 5 plus h squared minus 25 over h. Again, if I tried to put 0 in here, I'd get 5 squared minus 25, which is 0, over 0. And again, that's indeterminate, so I can't just substitute it in and find out what it is. It's this h on the bottom that's causing me some issues. So again, let's see if we can do some algebra here. This would be the limit as h goes to 0. Let's multiply this whole thing out. 5 plus h, when you FOIL it out, would be 25 plus 10h plus h squared minus 25 all over h. Now we're going to go ahead and collect like terms. Limit as h goes to 0 of 10h plus h squared all over h. So now what I notice is there's an h common to both terms in the top. So the limit as h goes to 0 of h times 10 plus h all over h when I factor that out. And when I factor that out, I notice, hey, my h's can cancel. So I get the limit as h goes to 0 of 10 plus h. Now I can do direct substitution. Now I can put the 0 in for h. The limit of a constant is just 10. The limit of h as h goes to 0 is just put the 0 in, so you get 10. Let's do another one. Again, similar idea, put 0 in, try plugging it in, see what happens. I'm going to get 16 square rooted, which is 4, minus 4, which is 0, over 0. So I get an indeterminate form. So I need to do some algebra on this. This algebra is going to be a little bit different. I don't like having square roots. I don't know what to do with them. And in past math classes, you were probably told to get rid of the square root at the top. You don't want those, but in reality, we want the square root in the top. We don't want this. We want to rationalize. We don't want the square root in the top. We want to rationalize the numerator instead of rationalizing the denominator. So we're going to go ahead and rationalize the numerator, and that means that you're going to take and multiply by the conjugate of the numerator. And whatever I do to the top, you make sure you do to the bottom. Now I can multiply that out and see what I get. When I multiply it out, make sure that you're multiplying out, foiling out the top. And I wouldn't foil out the bottom. You'll see why in a little bit. But I do want to foil out the top. So the limit as t goes to 0. Foiling this out, a square root times itself is just a thing inside. You're going to have the square root times 4 minus the square root times 4. So you're going to have basically the same thing, just the two terms are going to cancel. And then I'm going to have minus 4 plus 4, which is minus 16. All over, and again, I wouldn't multiply out the bottom yet. And we'll see what happens. We might need to multiply it out, but I doubt it. Now I'm going to collect like terms. I got a t squared up here, and a t times the square root of t squared plus 16 plus 4. Now I notice, hey, there's a t in the bottom, and there's 2 in the top, so one of those cancels. And so now I have, doing a little bit of algebra, limit as t goes to 0 of t over the square root of t squared plus 16 plus 4. Now if I plug 0 into the top, I get 0. And if I put like 0 into the bottom, I get the square root of 0 squared plus 16 plus 4, which is not 0. This is actually going to be 4 plus 4, which is 8. So I get 0 over 8, which of course is 0. So there's my limit. The next example I want to do is to show you that this limit does not exist. Remember, limits do not exist if the limit from the left and the limit from the right are not the same value. So let's go find out what the limit is from the left and the limit from the right. We'll start with the limit from the right. There's no reason to do it that way, but we will. So I have the absolute value of x minus 1 over x minus 1. We're going to come from numbers bigger than 1. So if we're coming from numbers bigger than 1, like 4 and 3 and 2, you're going to have 2 minus 1, which is 1, and the absolute value of 1 is a positive number. So you're always going to get, the number inside is always going to be positive, so the absolute value is the same as it. So if we're coming from the right, this would be the limit. As x goes to 1 from the right, of just x minus 1 over x minus 1. Because the absolute value is already positive. So you can just drop the absolute value bars. And we notice, hey, we get 1 here because you've got the same thing in the top and bottom. And the limit of 1 is, of course, just 1. Now let's find the limit from the left. So then we have the absolute value of x minus 1 over x minus 1, but we're coming from the left. So then again, you're coming from the left, so things that are smaller than 1, like -2 and -1 and 0. And each time you plug those kind of numbers in, you're going to get a negative number back. But the absolute value is always positive. So this limit, this number would have to be, the only way to make it positive is to take the x minus 1 and then take this the opposite sign. So it would be x minus 1 opposite negative x of x minus 1. And now I notice, hey, this is the limit as x goes to 1 from the left of -1, which given it's a constant is just -1. And now I notice the limit from the right is not the same as the limit from the left, so therefore the limit does not exist. Because the limit from the right and the limit from the left are not the same thing. So this is basic limits. There are some other things that go on with limits. Sometimes we have functions it's really hard to find out what the limit is. And one of the things that's kind of nice is that we can actually look at kind of what limits might be looking like. This one is basically telling us, this theorem is just basically saying that if function is less than another function, then as long as the limits exist, the limit from the one function is going to be less than the limit of the other. This leads us into a better theorem that we like to use called the squeeze theorem. And what it says is if we can put a function between two other functions, and we know the limit of those two other functions, then the limit of the middle one has to be L. Provided, of course, all these limits exist. And we use these when we have limits where we cannot find them any other way. So here's an example of a function I would like to find the limit of this. I'd like to find out what this limit is and what value we're going to get. And looking at this, I notice I don't know what to do with this. I can't use direct substitution because I've got the sign of pi over 0. If I use direct substitution, and of course you can't divide by 0. So that's not going to help me very much. So I need to figure out a way to do this without using direct substitution. I don't see an algebraic way to simplify this. So I'm going to use the squeeze theorem. What I need to do is get this function inside here in between two other functions. So one of the things to remember is the sign of anything. Whenever you take the sign of a number, that sign is always between -1 and 1. Remember, the range of a sign function is always from -1 to 1. So no matter what, the sign function is always between -1 and 1. So now let's see, what happens if I took this square root and multiplied by all three places? That would mean I would now have minus the square root of x cubed plus x squared is less than or equal to square root of x cubed plus x squared. Sine of pi over x is less than or equal to square root of x cubed plus x squared. All I did was just multiply every single term, every single piece times the square root of x cubed plus x squared. Well, that's useful. I wonder what that does for us. So this is kind of the squeeze theorem. This is now saying we have this part. We have the assumptions of the squeeze theorem. If this is true, so we have that. We have the if part. Now let's see if we can get the then part. So let's see if we can find the limits of this function, find the limits of this function, and hopefully they're the same value. So let's go find the limit as x goes to 0. Of negative the cube root of x cubed plus x squared. See what we get there. Now I can use direct substitution because I can put 0 into a square root. 0 cubed plus 0 squared is 0, and the square root of 0 is 0, and negative 0 is 0. So we get 0. And the limit as x goes to 0 of the positive one, x cubed plus x squared. Again, I can use direct substitution. 0 cubed plus 0 squared is 0, and the square root of 0 is 0. So both sides of these limits are 0, which means the thing in the middle has to have a limit of 0. So therefore, the limit as x goes to 0 of x cubed plus x squared sine of pi over x is 0 by the squeezed sum. And this is useful anytime you have a function that you can't possibly do any other way. If you can't use any algebraic techniques to simplify it like we were doing, you have to use the squeeze theorem to do this. And that's how we can find the limits algebraically, at least some of them.